Good afternoon. Please give us a few minutes to sort out a technical problem with the projector.
Todo isso.
Yeah, sorry about the delay. We still cannot see you on the projector, so we will all continue in Zoom, even locals. So I would like to introduce the first speaker of this afternoon session. So an ex-neighbor of mine. So it's Georgi Grachovsky from the Essex State University, from the University of Essex. I'm sorry. So, Georgi, can you hear us?
Yes, I can.
Yeah, if you could please try to, yeah, that's perfect.
Can you see my full screen?
So, yes, we can see your screen.
Okay, thank you, Sotiris. So the title of my talk will be Grassmann extensions of Young-Baxter maps, and this is based on
Georgi,
yeah.
why the conference is 2006?
Sorry. Sorry, I cannot.
I just muted Sasha accidentally. Sasha, please switch on your microphone. I accidentally muted you.
Yeah, 2016 is a amusing date for our conference. Now.
Oh, sorry. Sorry, a stupid mistake. I'm guilty for this. So that was the last night's exercise.
Okay.
First mistake.
Sorry? Anyways, it's based on a joint work with Sasha Mikhailov, who just spotted the mistake, and Sotiris Konstantinou from Yaroslavl. So the outline of the talk is that after a brief introduction, we'll set up the stage, so outlining shortly Grassmann algebras and Lax representations for discrete systems. Then we'll present the Darboux transformations for the Lax operators and the related discrete systems, and then we'll present the Young-Baxter maps for this the Darboux matrices. So main examples will be the Grassmann extended NLS and DNLS, and we will finish the talk with a brief outlook for possible for further extensions of this work. So as a motivation, I should say that non-commutative extensions of integrable equations have attracted the attention of the mathematical physics community for a very long time. So the non-commutative extensions for most integrable equations that we know, like Commutativity, Vries, Nonlinear, Schrödinger, Gordon, Kadomtsov, Petrishvili, Hirota, Miva, and so on. And the particular reason for such an interest is the supersymmetric extensions of such systems. That was a great topic in theoretical physics, starting from late 60s. And supersymmetric systems are particular examples of non-commutative integrable systems. Probably the best known example of such super extensions is the supersymmetric version of mkdV equation due to Manin and Radu. All the integrable aspects of these supersymmetric extensions are known and studied, including Soliton solutions, and the algebraic approach for obtaining such solutions are the so-called Darboux transformations, or the Dreising method. So actually the theory of the Darboux transformations was boosted by the Dreising method itself. I should mention here that Darboux transformations also play a role in constructing integrable discretizations of integrable equations. So the Darboux transformations themselves can be considered as Lax pairs of discrete integrable systems, and this is due to the Bianchi commutativity for Darboux or Backlund-Darboux transformations, and this fact is also known as principle for nonlinear superposition. That's why if one tries to classify elementary, in some sense, Darboux transformations, then this can be used as a tool to classify discrete integrable systems related to a given Lax operator. And as I just said a minute ago, such discrete systems will have a Lax pair provided by a set of two consistent or Bianchi commutative the Darboux transformations. And the corresponding background transformations will represent the symmetries of these discrete or different systems. So our object of study will be a supersymmetric version of the nonlinear Schrödinger equation introduced by the late Piotr Kulish. And this is related to the autosymplectic superalgebra of rank 2. And here the Greek letters, well, all the functions are assumed to be sufficiently smooth or differentiable as many times as we need. And the Latin letter, the Latin letter is related to bosonic or commuting variables, while the Greek letters here are called anti-fermionic variables, so they anti-commute. And having said this, actually, this property of having both commuting and anti-commuting variables actually splits the underlying superalgebra into two parts, so in the bosonic part and the fermionic part. And this is actually due to the fact that there is a natural Z2 grading, in our superalgebra. So this involutive automorphism that introduces this grading condition, and those elements that belong either to one of these subspaces are called homogeneous. So the generic element is usually a sum of two parts, sum of bosonic and fermionic parts. And so we say also that the bosonic variables have even parity and the fermionic parts have an odd parity. And Grassmann commutativity simply means that the commutation rule actually depends on the parity of the elements for homogeneous elements. And in particular, if you take a square of fermionic variable, you will get identically 0. So in other words, you can have only linear combinations of fermionic variables. And now if we go to our main object, the supersymmetric version of this nonlinear Schrödinger equation.
If
And,
you need,
I'm sorry, there is a noise coming from outside. So if we start with the Lax operator, having the standard form, so the differential operator plus a potential, and here lambda is a spectral parameter which introduces the grading in the algebra, so it must be an even variable. And now the potential matrix is assumed to have entries from a Grassmann algebra. So Greek letters are the commuting functions, anti-commuting functions, and Latin letters are the commuting functions. So P and Q are even elements. And we'll assume that the Greek letters are homogeneous elements. And we'll be using the standard nature of grading on the Grassmann algebra. And by the Darboux transformation, we will understand the map that acting on a Lax operator is just updating its potential with new values. And also we restrict ourselves to the class of rational Darboux transformations. And if the Deluxe operator satisfies, so if the eigenfunction of the Deluxe operator, if we have an eigenfunction of the Deluxe operator, then the dressing, the Darboux transformations should satisfy this equation, because of the so-called dressing chain. And then we should mention also here that Darboux transformations form a group. So composition of Darboux transformations is again a Darboux transformation, but with more complicated rational dependence on the spectral parameter. And now we can say what precisely do we mean by elementary Darboux transformations. So we understand by elementary Darboux transformations such Darboux transformations that cannot be decomposed further. So this means that we can restrict ourselves to linear Darboux transformations, and then we can classify them by the rank of the matrices. So if we substitute this in the dressing equation, we will get a set of 3 equations. So the dressing equation is a polynomial, dressing chain is a polynomial in lambda. So we'll have a lambda independent term, a linear term, and quadratic term. So then I can solve this recursively. So the lambda term will give you some restrictions on the potential matrix. So this means that we can take the Darboux matrix in this form. And then the lambda independent term, the free term, will produce a set of algebraic constraints. And this is the first case where this element here, the 3 element, is 0. So in this case, the dressing chain explicitly takes this form. So again, all Latin letters here are even variables and all Greek letters are odd variables. And if we make a change of variables, we're introducing new variables, phi, psi, and v. And by subscript -1, we'll understand the backward shift, why subscript k in general means k shift k times. So if we make this change of variables, actually one can eliminate the function that appears here, the function capital F, and as a result, you will get this equation for the dressing. So it looks familiar, and actually this is the non-commutative extension of the famous Toda chain. So if we set all the Greek letters to be 0, we'll get exactly 100. And the system has a Lagrangian formulation. The Lagrangian function is written over here. And indeed, once again, if you set all the Greek letters to be 0, you'll get the total. Then there is another case. There is another case where the Darboux matrix has a maximal rank. And due to Abel's theorem, the Wronskian must not depend on X. since the potential is traced matrix. And that's why we can show that the function capital F in this case is an integral of motion. So as a result, we can use it a constant value there, and we can write the Darboux matrix in this form. Should note here that the algebraic constraints here coming from the x-independent term have much more compact form now. But you can see that you have one minus the shift operator, so which means a fine difference. And in this case, the dressing chain will take this form. And you can see that because of the algebraic constraint here, if we express the Greek variables, there will be actually the inverse of this operator acting on the right-hand side. So as a result, you will get the inverse of 1 minus t. And this produces a non-locality of the dressing chain. So it's like having an integral in the continuous equation. Sorry. I should mention also here that this dressing chain can be written in terms of only in a local form by a change of the variables, but the resulting dressing chain, the new variables, will be non-evolutionary form. So there is a price to be paid. So this dressing chain is known as the NLS dressing chain, nonlinear Schrodinger dressing chain. And indeed, in a bosonic limit, it reduces to the standard nonlinear Schrodinger dressing chain. And now the main object, here we finally arrived there, is the Young-Baxter map. So the Young-Baxter maps originate from the set theoretical Young-Baxter equation, and the motivation for this is so-called quantum Young-Baxter equation, or the factorization equation for scattering matrices. So if we have a linear operator acting on tensor products of vector spaces, then the Young-Baxter equation is actually this kind of refactorization equation. And if and our maps actually act now on the triple tensor products. And then a solution of this equation is known as Young-Baxter map. So I should say that having refactorization type of equations of this form is a very restrictive condition. So it's even a miracle that this can have a solution. So it's very, very unusual. And so I mentioned that Young-Baxter maps are just the solutions of this set theoretical Young-Baxter equation. And now, if we consider a map like this, where updates the variables x and y to a new variable u and v, and if we consider the functions for which we will construct Young-Baxter maps in the following way. So having index I and j, it means that it acts on ith and jth element of this ith and jth component of this vector space. So having y1, 2 means that we act only on first and the second component. Having 1 and 3, it means that we act on the first and the third component. and so on. And then the map is called Young-Baxter map if it satisfies the Young-Baxter equation. And if in addition it satisfies this property, usually it's called a reversible map. So in general, there is no reason to be the birational maps in general. And the next thing is that we can also consider Young-Baxter maps depending on additional parameters. And in this case, this map will satisfy the parametric version of the Young-Baxter equation. So for every variable, if you have a corresponding parameter, then this permutation will depend also on a parameter that stays for the corresponding component. And one can represent parametric Young-Baxter maps on a quad. So if you associate with the original variables x and y the sides, and you add the corresponding parameters, the map will actually map it to the opposite sides that complete the squad, having a new variable u, new variables u and v. And the Young-Baxter maps can be associated with the diagonals. And in this case, if you decide to construct a cube out of this map, and you require that the consistency around the cube, this will result to the parametric Young-Baxter equation. And there is a very classical example of this. First, so one can construct Young-Baxter maps for integrable systems. And for instance, if you consider the discrete KdV equation, then you can associate with the function, the shift in the horizontal direction, the shift in the vertical direction, and the composition of the two shifts. Actually, two variables, x and y, and so x and y and u and v. And u and v will be actually the images of the Young-Baxter maps. And then if we set the differences of the values on the corners to be the values of the side of the quadrilateral, we will get this condition. And as a result, we will get this property. And if we solve this with respect to the new variables u and v, we will get explicitly the Young-Baxter map that corresponds to this. So this will be the new variables u and v, and this is known as Adler map for discrete KdV equation, which is again on the Young-Baxter map. And now we go to our main part. So we'll call the matrix our Lax matrix. Sorry? So we'll call this a Lax matrix for the parametric Young-Baxter map if it satisfies the following refactorization problem. And if this problem is uniquely solvable for u and v, then the resulting solution is a reversible Young-Baxter map. So we'll use Darboux matrices as Lax matrices for our discrete systems. And we'll try to we'll present the non-commutative extensions of these Young-Baxter maps. And for example, if for the Adler map we take a Lax matrix in this form and refactorization problem in this form, indeed the unique solution will be the Adler map. Now for our discrete systems, if we consider a discrete system with a maximal rank, then the corresponding algebraic variety is a union of two 10-dimensional components. And the first one comes from a refactorization problem, and it corresponds to the permutation map, which is trivial as a Young-Baxter map. But then the second one is a non-involutive birational Young-Baxter map. It has 10 components. Then we can see here that if we take these two quantities, they're actually invariants, or the analogs of first integrals for this map. And because of their existence, one can restrict this 10-dimensional map to an 8-dimensional map, and on the level sets of the first integrals. And if you take a bosonic limit of this, this is the known Adler-Yemilov map. And now if we introduce non-commuting variables, so Greek letters are again non-commuting variables. In this case, the exact solution, the exact Young-Baxter map, will have this form, and the invariants will have this form. So if you take a bosonic limit, we'll get exactly the Adler-Yemilov map. And of course, here we'll skip the additional constants, since they just shift the symplectic leaves. And these invariants are actually linear combinations of the following integrals. And these integrals are in involution with respect to the Poisson bracket, the canonical Poisson bracket. And all the other Poisson brackets are trivial. And the corresponding Poisson tensor matrix is invariant under the Young-Baxter maps. For the Grassmann extended Adler-Yemilov map, we need to know that the last two integrals are actually functionally dependent. So if you square the third one, you will get twice the fourth one. And I'm about to finish now. So the result obtained here can be actually developed in several directions. For example, to other integrable hierarchies, to study the whole hierarchy, there to study the corresponding non-commutative and twining Young-Baxter maps and their transfer dynamics. And probably I should stop here, and thank you.
Okay, thank you very much, Georgi. So, are there any questions or remarks?
I have a remark.
Okay, there's a remark by Sergey. Let
Okay,
me
so,
just pass the microphone.
At some point, you said that from the refactorization property, you get. I switch on off. Okay. Right. So when you explained Lex equations for Young-Baxter, you said that if a Lex equation is uniquely solvable, then automatically you get Young-Baxter property, right? Actually, you need some extra condition. You need some uniqueness of three factorization.
But by Lax equation, I mean the Lax-Darboux equation for the refactorization problem, for the Darboux matrices. I don't mean the zero curvature equation.
I understand. I just want to say that when people say about connection between Young-Baxter and Lex equations, they often forget that you need to consider the three factorization property also.
Yes. That's what I mean by Lax-Darboux equation. I mean the refactorization equation for the Darboux transform.
Okay, there is some additional 3 factorization. You need to require uniqueness of 3 factorization.
Ah, okay.
It is satisfied.
I can't hear.
I say that it is satisfied in this case.
Yes, indeed.
So the question is if you get the 3 factorization, if you will get the unique solution.
So
that was actually the reason. There's some kind of loop. I don't know why. Anyway, so the question is.
I think the question is has been solved.
So if the 3 factorization gives you the trivial solution.
Well,
Yes, it does.
so I mean, no. Well, I think in the talk, the speaker forgot to mention that in order to derive Young-Baxter property from refactorization, you need to require uniqueness of 3 factorization.
Yeah, the 3
Must imply, and you get Young-Baxter.
The 3 factorization does imply trivial solution, in other words. Yeah.
Okay.
So, are there any other questions or remarks?
I would like to ask something, Sotiris, if possible. I don't know if you can hear me.
Yes, Sotiris, of course.
Hi, Georgi.
Hi.
Can I ask you if about this Poisson bracket in this Grassmann algebras? Is it? I mean, is it okay to define a Poisson bracket in a similar way as in between a commutative and non-commutative?
The difference is that you can do it in more than one way, and the sense of canonical, being canonical, is a bit relaxed or a bit vague.
Okay, thank you.
So there is this definition of Poisson bracket for if you have a commutative and anti-commutative variables at the same time. I can give you a reference.
Okay, thank you.
So, any questions or remarks?
Sotir, can I ask something?
Yes, of course.
So then this means that the real integrability in the Grassmann setting is well understood, or what?
It's on the way to be well understood.
Okay. Okay.
Yeah. Any other questions or remarks? Okay, in which case we would like to thank the speaker again. Thanks very much. So the next speaker for today is Yota Adamopoulou from the Hero University, and she will be talking about on a hierarchy of multi-component generalization of data equations. So Yota, I don't know if you can hear us.
Yes, I can hear you. Just tell me, do I just to share my screen?
Yes, please.
Yes, okay. So hang on a second. Tell me if I'm doing this right, because I've never done this before.
Who will tell you if you're doing this wrong?
Hang on. Can you see me as well?
Yeah, you now.
Okay. Now you can hear me. Can you see me as well?
We can see you. Yeah.
Okay. Sorry.
We're very grateful if we could also see your slides.
Yes. Give me a second. Hang on.
Something is going. Yeah, that's perfect. We can see it now.
Can you see it now?
Yes, perfect. Thank you.
Not the background of my screen, just the slides, right?
No, and the messages that they are sending you.
Messages?
Yeah, we see the slides. I'm joking.
Okay. All right. So hang on a second. Okay, so thank you very much, Sotiris, for the invitation to speak at the second international conference on integrable systems and nonlinear dynamics. It is really a shame that we couldn't come to Yaroslav, because that would have been one of the nice parts of the conference. But unfortunately, the situation being as it is, we have to stay on the island here and bear with the weather. Okay, so what I want to discuss today is some results we obtained with George Papamikos some time ago. So let me actually, yes. So that were published in the beginning of the year and relate to the construction of the hierarchy of a vectorial generalization of the modified KdV equation. So, I'm sorry, do you see the slides moving forward? I hope you can. Okay, so the outline of the talk is as follows. So first I will discuss, I will say a few things about the modified KdV equation, since I will be discussing then a generalization of that equation, the vectorial generalization of mkdV. And I'll say a few things about its lax representation. And then in the second part, although it's misleading, bullet point 2 is part 1. So there I will say a few things about how one can construct the hierarchy of this vector mkdV equation based on the ideas of now classical ideas of Drinfeld and Sokolov. And then in the last part, I will discuss some solutions, how one can find solutions to the whole hierarchy, and basically I'll discuss the soliton and breather solution. Okay, so first part, the mkdV equation, or modified KdV equation. It's an equation, I don't know if you can see my pointer, I hope you can. So an equation for the field U that depends on T and X, subscripts denote derivatives as usual. And it has this quadratic non-linearity. So this was first solved using inverse scattering, actually, and by Wadati in 1972 and 73, where he also obtained the n-soliton solution for the equation. Before the solution of the equation via inverse scattering appeared, Miura introduced the now famous Miura transformation. So this one here, which relates solutions to the modified KdV of the modified KdV equation to solutions of the KdV equation. That is here, the equation for W. I mean, basically the mkdV equation is an integrable equation. Okay, so that's the first thing I should have mentioned anyway. So it's of particular interest, especially for this conference. One of the characteristic properties of an integrable equation is that it has an infinity of conservation laws. So basically expressions of this form over here, where the capital F's are the densities and the capital G's are the fluxes. And it was Miura, Gardner, and Kraskal in 1968. So actually the paper that followed, if I remember correctly, this paper in the same journal, but okay, that's with a question mark. So they found, they showed that mkdV has an infinite number of conservation laws, and they also calculated the first few conserved, the first few densities and fluxes. So for example, the first density is U, and the first flux is this one, so minus UXX, second derivative of U with respect to X, minus a half U cubed. Which is basically the equation itself. So it's an integrable equation. It admits a lax representation. And Ablovitz, Kaup, Newell, and Segur in 1974 formalized the now known as AKNS scheme, where they wrote down 2 by 2 matrices such that, so U and V, let's call them here, such that the compatibility condition of this overdetermined system of equations is actually equivalent to the mkdV equation. And now via the AKNS scheme, they showed also a relation to the sine-Gordon equation, so this equation here, and the NLS equation. One thing to mention is that here the matrices U and V, so one of them is linear in lambda, while the other one is cubic in lambda. Okay, so let's move on to the vector mkdV equation. So here in this talk, I will discuss this generalization, this vectorial generalization, where now U, boldface U, has n components, U1 up to Un. Again, it depends on x and t. And this here denotes the standard Euclidean, well, it's U transpose times U. Now, for n equals 1, we get the mkdV equation. And let me mention here that actually many generalizations of the mkdV equation have appeared and have been studied by many authors. For example, by Fordy and Collabo, by Sokolov. This particular one appeared in the works of Jingping Wang and Jan Sanders. And they also wrote down the lax representation for this equation over here. In the same work, they also found the recursion operator and the Hamiltonian structure, which were also studied by Anko a bit later, a couple of years later, who also in a different paper studied the 1 and 2 soliton solutions for the case where n is equal to 2. Also, Mikhailov, Papamikos, and Wan studied the sine-Gordon equation and discussed relationship between the two. And one thing to mention here is that actually this vector mkdV equation is not the vector mkdV equation that appears in the vector AKNS hierarchy as one of the two terms. So this term we don't have in the equation over here. So it's a different one. Okay. Now for the lax operator, the one introduced by Jingping Wang, Sanders, and Marie Beffa has this form. So we're looking at n+2 by n+2 skew-symmetric matrices, J and U. Here this block is SON, and U is linear in lambda. Also, the lax operator is invariant under these three transformations. So it has these symmetries. Well, the first one relates, so the R relates to the fact that J and U have real entries, and the T is that they're skew-symmetric matrices. And we also have this Q transformation here, which we will be using later on. So these form a group, the well-known reduction groups introduced and studied by Mikhailov and others back in the 1970s. So, sorry, I can hear something, please. No, okay. So it turns out that actually this last symmetry over here, the Q transformation induces a Z2 grading to our algebra, so SON+2, and I can split it in the odd and even elements. So the even elements are those such that this conjugation with Q leaves them invariant, while the others, the G1 is those that get a minus sign in front. And we did see a few other talks in this conference where such decompositions were discussed as well. So the odd elements in our case are those of this form over here. So J is odd, and the even elements are of this form, which means U is even, and this is an n by n matrix. We also introduce we define the map, the adjoint J map, and it turns out that the kernel of adjoint J has elements of the form over here, where this block up here is basically elements spanned by J, and we also have this non-trivial n by n block down there. So this K is a non-abelian subalgebra of G, and if we introduce the zero and odd parts by taking the intersection with the 0 and odd elements of G, then it turns out that we have these nice relations, and I mentioned this here because I will use this later on. Okay, now they just seem out of the blue. And we also introduced the image of a joint J and also the odd and even parts of that. So why do we need all this? Well, in order to find the hierarchy of the vector mkdV equation. So as I mentioned earlier, I'm not giving explicit citations, but basically we'll be using the Drinfeld and Sokolov ideas. So what is the hierarchy? It's the set of all compatibility conditions of these systems of equations, where the AK are operators of this form. So basically I can rewrite so this is the compatibility, and I can write it down in this form, in the lax form. So the question is, how can we find all such VKs so that this lax equation is satisfied identically in lambda? And the very crucial observation is that the left-hand side of this relation, so dt of L, of the lax operator, has this form, over here. So this means it's in the even part of the image of a joint J. So in other words, it's lambda independent, it's Q-symmetric, and it actually, so basically what I'm looking for is the V's, so that the right-hand side is also lambda independent, Q-symmetric, and exactly the same form as this. Okay, so the starting point would be to look at formal, so series, A lambda, we call them here, which are invariant under the transformation Q, and so that the coefficients in lambda are elements of our algebra. And I will also consider the projections to the positive in lambda and purely negative powers in lambda. Now, if this series, if this A of lambda commutes with my lax operator L, then I can rewrite this expression in this form over here, whereas actually on the left-hand side is polynomial in lambda, while the right-hand side has strictly non-positive powers in lambda. So basically what I'm looking for is the A such that, so the formal series A such that the projection to the positive lambda part is equal to this, so lambda independence Q-symmetric and same form as dTL. So I want to determine this A of lambda. Okay, how do we proceed to determine this? Well, I start from the starting point so that A commutes with L, and I can rewrite this using the form of L. I can rewrite this in this form, and then basically this equation one could solve recursively for by matching powers of lambda. It turns out that when K is odd, then AK is equal to J, which means the series A lambda have, so the coefficient of lambda to power K is equal to J. Now, if K is even, then we get non-local equations, but that's something I'm not going to discuss now. So we stick to K odd. Now, I can write A in this form as this product here, where P satisfies this differential equation, and C is a constant matrix. And now we see, P has this asymptotic behavior. And now if I set P to be equal to M times the exponential, so the asymptotic behavior, and then I plug this back into my equation for A, then I can find that M satisfies this equation, and it's of this form, basically, so only negative powers in lambda. And M, we want it also to be orthogonal and invariant under the symmetry Q. So this relation here, I can rewrite if I introduce the operator L0, which is, so it's basically the operator where U, the field U is equal to 0. Then I can rewrite this in this form, which means this matrix M is a formal Darboux dressing matrix for the vector mkdV hierarchy. And now going back to my V, it turns out that I can write, so V is basically written down in terms of M in this form. So if I want to find the V's, I need to determine M and C. Okay, one thing that will be useful in order to find the conservation law for deriving the conservation laws is to factorize the Darboux matrix. And here I factorize it in terms of W and H that have this form. They're also equal to identity plus 1 over lambda powers. And also H, my H commutes with J, basically. Now, if I plug this into the equation for M, I get an equation for W and small h, where small h is given by this relation here. And it's actually in the kernel of adjoint J. And now, if looking at this relation, if I compare powers of lambda, then I will get equations for the coefficients of W and small h. So I get this equation, which I can solve recursively for H and W, Hi and Wi, so I can determine all of them. Which means, so how long do I have? Right. So this means that so far I know that the VKs are given by this expression. I know that I can factorize M. And I know that the leading coefficient of the power in lambda is J. Now, if this C over here is actually exactly equal to lambda K times J, then it turns out that first of all, I can rewrite this expression in this form. And the W I know because I have calculated all the terms recursively from earlier on. And also, if C is equal to this, then its Lax equation. So bottom line, I have determined V, okay? This is my V, and I know how to find all the W's. Also, and this is for K odd. Also, each of the Lax equations, so for each value of K, has this symmetry over here, okay? This one over here, no, okay. So let's have a look at a few examples. So for example, when K is equal to 1, by using the relation that I had above, by solving it recursively for the Hi and the Wi, I can calculate W1, and it basically turns out that V1, so the first, so the Lax matrix for the first member of the hierarchy is basically equal to U, so the U that appeared in my L Lax operator. And now the Lax equation, or the compatibility condition between L and A, basically give the first element, the first member of the hierarchy, which is this equation over here. Now I can move on. When K is 3, next member, it turns out, well, that this is the vector mkdV equation that I was looking at earlier. And it has cubic dependence on the spectral parameter. Okay. Now, one thing one can also show using the Drinfeld and Sokolov ideas is that the flows, so all the flows generated in the way I showed previously commute. So these are known ideas, so I'll just skip through these very quickly. We derive that the flows commute by using the Lax equation, and the fact that M is a Darboux matrix, so it satisfies this equation. Then we can actually show by using also the Jacobi identity that the flows commute. So I'm not going to give any details here because this is just technical actually. Now, as I mentioned earlier, the recursion operator of the vector mkdV associated to the vector mkdV equation was derived by Jinping Wang and collaborators, and by Anko and collaborators. So here, what we've done in this paper, we have derived it using ideas by Sokolov and collaborators. So we basically use the Lax equation and the reduction group. So the first step is to split the V operator in this form. So one of the the Lax operators in this form. And then by using the Lax equation and comparing basically powers of lambda, and the fact that, so I've used the reduction group, so I'm looking at even and odd elements here, then one can solve the Lax equation for this capital A and capital B, and we can express this in terms of U, and we can also find this recursive relation between members of the hierarchy, where R is the recursion operator, and it's given in this formula over here. Let me just mention that also one can write down a recursive relation for the Lax matrices. I haven't written this down here because it would take up too much space, but basically by using these ideas over here, so following from this equation, one can do that as well. So if I can derive some of the equations of the hierarchy using the recursion operator. So if I start from the first one, so the first equation is basically ut is equal to ux. And if I act on ux by r, then I will get the vector mkdv equation. And we also derived the next one, the fifth member of the hierarchy, by acting with r on the vector mkdv equation itself. Okay, so did I run out of time already? Or I started later, right?
Yeah, yes, you started a bit later.
So how long do I still have?
And I'll tell you, you have at least 5 minutes because we started late.
Okay, okay, thanks. Right, so conservation laws. So this is important. And as I mentioned earlier, the factorization of the Darboux matrix will help us derive the conservation laws. So again, we're using the Lax equation and the Darboux matrix and its factorization, the equation for the Darboux matrix and the factorization. And it turns out that the Lax equation can be written in this form. Now, if this last term wasn't here, then I would immediately have a conservation law. And it actually turns out that this term is 0 when, well, for odd k, because the element 1, 2 of the of H, so, and I'm talking about the matrix H, is basically a generating function of the conserved scalar densities of the hierarchy, and these vk tildes, so the 1, 2 element again, will give the corresponding fluxes. So, and this is for k odd. So, for example, the first conserved density is this one, that's the second one, and so on. One thing to mention is that in this case, the mass, the conservation of mass basically disappears. So we don't have a U. And that's something that was noted by other authors. So Anko was the first one to mention this in his 2006 paper. And another thing to note is that we have also derived a matrix conservation law, which it basically relates to, so when k is equal to 2, because for higher even values of k, we don't get any conservation laws. And the corresponding densities have this form over here. So this basically comes from the bottom SON part of the Lax representation. Okay, one special case, and then I'll probably just skim through solutions very, very quickly, is what happens when we consider the SO4 case. So in this case, I get, so I have two fields, so n is equal to 2 in this case, two fields, which means I get the complex mkdV or Hirota equation if I consider V to be U1 plus I U2. The nice thing about this is that we can derive a member of the, well, the NLS equation basically is a member of the hierarchy in this case, although the NLS equation has quadratic dependence on lambda. And this all boils down to the fact that this this matrix here in the bottom of the lax, yes, of the lax matrix, V is basically SO2. So it's, well, I have one-dimensional kernel in this case. So I have an abelian, sorry, kernel in this case. And just a note here that also, and this was actually noted by Jinping Wang, that in this case, the recursion operator can be read for the mkdV hierarchy, vector mkdV hierarchy can be written as a composition of the recursion operators for the NLS hierarchy. Okay, so for solutions now, very quickly, we basically construct exact Darboux transformations such that these systems of equations remain form invariant. Now, and by form invariant, I mean that they retain their form, but now L and A depend on the field U tilde, which is the so-called dressed field. So from known solutions, we want to obtain new solutions. Now the matrix M satisfies the so-called Lax-Darboux equations, which are these. And if we make the assumption that it also satisfies these conditions, so then this requirement is in line with the requirement in line with the fact that my Lax operators are invariant under the reduction group. Now, for the soliton solution, we consider a Darboux matrix that has a simple pole, and it's basically of this form over here. So simple pole at lambda equals mu, and then by using these previously mentioned expressions over here, I can derive that overall my Darboux matrix has this form where P is a rank 1 projector, and it can be written in terms of n+2, in terms of this n+2 dimensional vector Q that also satisfies this condition over here. If I look at the Lax-Darboux equations, so I have a form for the Darboux matrix, which means I plug it in my Lax-Darboux equations, and then I can get one of the expressions that I get is this one, the dressing relation, where U tilde is the matrix that contains the new field U tilde, the small U tilde. And this means if I solve U tilde in terms of the rest, I can express it in terms of the elements of the Darboux matrix. So the elements of the vector Q that I have expressed my Darboux matrix in terms of. Now, how can I find this, the Q? Well, it turns out that it satisfies, it's a solution to the overdetermined system of equations when lambda is equal to I mu. So I can express it in terms of the fundamental solution of the system. So let's say if I start from the trivial solution, U equal to 0, then I can solve this for the system related to these operators. For psi takes this form, which means then I can express my vector, my vector Q in terms of this solution, and hence express find the one soliton solution for the vector mkdV hierarchy. Let me mention that this is for the whole hierarchy because this sigma here contains all the times for the hierarchy, okay, so for k odd. And now I'll move forward. Okay, this is just an example. I'll forget about this for now. Now for the breather solution, I consider my Darboux matrix to have generic simple poles at these values for lambda, so generic points in the complex plane, complex lambda plane. And now if I consider, again, the assumptions that I had for the Darboux matrix, I have this form over here. And now in the simplest case, so now P and Q, these are not vectors anymore, but they are matrices, which means, well, I have some additional structure. I can write down the simplest case. So in other words, when P and Q are vectors, and by doing that, we basically have derived the breather solution, the rank 1 breather solution for the whole hierarchy, which is given here by this formula, where this delta contain the vectors, elements of the vector Q, which I can express in terms of the fundamental solution of the linear system of equations. So I've cheated here, I've used the simplest case. Well, that's basically one field. This is what the breather solution looks like. So it's the trivial case. And that's all. Thank you very much. Sorry for going very quickly through the last bit.
Thank you very much, Jota. Are there any questions or remarks? No questions from the audience. Any questions from the online participants?
No. Okay.
That means that everything was quite clear.
Well, I hope so. Okay, thank you very much.
Thank you. So we're ready to move to the next speaker for today. So I don't know if he's online. He's probably is. So the next speaker for today is George Papamikos from the University of Essex. I don't know, George, can you hear us?
Can you hear me?
Yes, we can hear you and you can see you.
Wait, let me share. Can I share now?
Yes, you can share, but
Can
make
you see
sure
this?
to close whatever you don't want us to see.
Okay.
Yeah, you can see your slides now.
Can you see
Yeah. And they are moving as well. So
okay, cool,
great.
cool.
So Yorgos, you will be talking about such theoretical solutions of the Young-Baxter equation and their associated integrable maps. So Yorgos, please start.
Okay, cool. Thanks for the introduction and for the invitation. Certainly, it's good to participate to a conference while the world has changed a lot. So that's a nice change of pace. Maybe next year we'll be coming actually to Yaroslav and have the same conference in person. Okay, so this is I have talked before about related things. So here I want to just in this talk to basically that's kind of the plan. We'll give an introduction, some definitions. Already some definitions have appeared in the previous talks, but then I want to go in detail in example the Adler map, and then I want to show you some ideas, some results, which basically I obtained because I kind of wanted to understand how Young-Baxter maps can be used for continuous systems or continuous integrable systems. And I mean, what we know up to this point, it's not, I would say, completely satisfying. So, I'll say a few things. Maybe there are something deeper. We'll see. And then in the end, it's in the fourth part of the talk, I will say about some actual results that have been published in collaboration with Sotiris, with Sasa, with Jinping. And I will talk also about some other ideas and some perhaps open problems that we're looking at the moment. Okay. So let's start with the introduction. So we will be talking about integrable maps, and an integrable map in analogy with a continuous system. I would say roughly it's integrable if it has enough invariants, but there is a twist in discrete case, and the discrete case is that basically even for a one-dimensional map, you can have chaos or non-integrability. And here, for example, let's see an example. So in 2 dimensions, we have this map, which of course it's like kind of inverse engineered just to make a point. So this map has this invariant, which I can use to reduce the order of the map and also fall to the logistic equation, right? Which is known to have chaos for for large values of age. Okay. So to assure integrability, then you need more information, right? And usually people are talking about measure preservation or Liouville integrability. So they introduce some kind of Poisson symplectic structure. And usually, well, other they say, well, integrability in terms of lax representation, which actually can be used to produce invariants. And then there is the kind of the analog of the Penlevé property, which is called the singularity confinement and log complexity growth. In this talk, we'll be focusing mainly on lax pairs and Poisson symplectic structures, okay, as a kind of definition of integrability. So Liouville integrability then, by now it's well understood. Goes back to the work of Veselov and Ruskin, Ranisko. These are classical papers. So basically you have, when you were talking about iterations of a map from manifold P to P, so this defines a discrete dynamical system, and we say that F is Liouville integrable if P is a manifold of dimension 2n plus m, and admits a Poisson structure of 2n rank. If the Poisson structure, if there is invariant under the action of the map, so the map, the discrete map should be Poisson, right? So in analogy with symplectomorphisms, right? And the map F admits n plus m invariants. The m is the number of Casimirs, okay, which all Poisson commute. So let's talk about Yang-Baxter maps. So we heard this before today. So this is the quantum Yang-Baxter equation. So R is a linear map from A tensor product A to A tensor product A. And these are Rij are the extensions of the map acting on a specific component of the third triple tensor product. But we will focus on set theoretic solutions of the Yang-Baxter equation. So instead of having tensor products, we'll have Cartesian products and compositions of functions, right? So R will be then a map from A Cartesian product A to A Cartesian product A, taking X and Y to U and V. So U and V are functions of X and Y. So the extensions look like this. So R12 leaves the third component invariant and acts on the first and the second as normally as the map R. Okay. Similarly, R13 leaves the second component invariant and acts on 1,3 and in the variables x, z. Okay. And similarly R23. Let's see an example. So if we consider this map of a spatial form, so f of x comma g of y, then these are the extensions. If I calculate the left-hand side of the Yang-Baxter equation, I get this. This is the compositions of maps. If I calculate the right-hand side of the Yang-Baxter equation, I get this. We see that the first component is identically the same with the first one. The third component is identically the same with the third component, so no complaints there. But here there is a difference. So basically it follows that R is a Yang-Baxter map if and only if F commutes with G. Okay. Of course, now, well, what's the point of this example? I just want to tell you that in the simplest case of this example, it just imposes the commutativity of these maps. But in general, if you have general functions, it will be some kind of complicated equation for compositions of maps. Okay. In the integrable side of things, we usually denote the Yang-Baxter map in the following way. So we have a square and we put the fields on the edges, right? And from X and Y, we go to U and V. And well, the Yang-Baxter equation can be represented as, again, it was discussed previously, as a kind of compatibility around the cube. So basically, if you put if you extend this picture in 3 dimensions and you put the initial data in these edges, X, Y, and Z, then you can calculate X prime, Y prime, and Z prime in 2 different ways. If these 2 different ways agree, then you get a solution to the Yang-Baxter equation. R is a solution to the Yang-Baxter equation, okay? And then there is the concept of parametric Yang-Baxter equation, or a parametric Yang-Baxter map, which is a solution of the parametric Yang-Baxter equation. So basically here you just assign to the specific edges also a parameter, A, B, and C. So A is attached to the edge, which corresponds to the variables X, B to the variable Y, and C to the variable Z. So maybe if I go back, we'll put in this direction, in this edge, the parameter A, in this here we attach parameter B, and here the parameter C, okay? And then we have the definition about the refactorization problem or the lax type equations that are related to Yang-Baxter equation, to Yang-Baxter maps. So if the refactorization problem has a unique solution for U and V in terms of X and Y, we say that L is a lax matrix for this map, right? But here, up to this point, we don't say anything about Yang-Baxter maps. But then there is an extra condition. So I think this is the condition that was Igoni was talking before. So if this triple factorization problem has the trivial solution, then we get that the obtained map from this refactorization is a parametric Yang-Baxter map. Okay, so this appeared, I think, formally first here in the paper of Kouloukas Papayoriou, but I think it was known to Veselov perhaps, or it was mentioned in Veselov, I think. Now, if we assume that the refactorization problem, the Lax matrix is invertible, we can define this what we call the monodromy matrix, and we can see that basically under the map, the monodromy matrix is related to M, so the advanced M is related to the old M by just a similarity transformation, which means that the eigenvalues are conserved, or the characteristic polynomial can give first integrals. More generally, if we don't assume that L is invertible, we can just take the trace of this here relation, and basically the trace will just give, it's a generating function of invariance for the map. Okay. Then we have some other nice properties. So we can see that the refactorization problem admits this symmetry. So if we exchange U with Y and Y with U and V with X and X with B and the parameters A with B, then this equation remains invariant, which basically says that if the Yang-Baxter map is a rational solution, then of the refactorization problem, then the inverse map will be also a rational solution, and actually of this form, where P is this permutation operator. In particular, we're dealing with birational maps, okay? So very nice maps, invertible. They can have a forward evolution, a backwards evolution. Yes, they're well defined. Let's see an example. So this is the Adler map, again, previously mentioned in the previous talk. It has these properties. Okay, so in this case, this map is also involutive. It comes from a refactorization problem. Okay. If we define the monodromy matrix, we can take its trace, and we find that the Adler map has this invariant. But now, as I mentioned, this is an evolutive map, right? Which means that okay, the points are confined over the level sets of this invariant, but then it means probably there are other invariants to make the map involutive, right? Because this in principle would say that an orbit here would go to infinity. And indeed, there is also another invariant. This one, you can see it's an invariant. And basically the way I constructed this just by taking a group averaging over the orbit. So for example, in particular, if I average over the orbit this function here, then I get the I2 invariant. So basically we can define these extensions and we can really see that it satisfies the parametric Yang-Baxter equation. Okay, so Adler map is a solution of the parametric Yang-Baxter equation. But now we can do something else. So we can define the triple refactorization problems. And here I'm using the lax matrices. I'm focusing on the kind of Adler case. So I'm using these lax matrices of the Adler map, and I'm considering these three refactorization problems. And then uniquely these problems, these refactorization problems define three maps, okay, which I will show you. I think these are mentioned in the paper of Veselov. They're the simplest transfer maps, okay. So these maps, so this is R1, it's birational. This is R2, again birational, R3 birational. They're fairly more complicated, but you can see that effectively, so X bar goes to Z plus something, Y bar goes to X plus something, the same for Z bar. So in some sense so when the parameters go to 0, you'll just get a permutation, right? So this is kind of a rational deformation of the permutation, okay? So all these three maps admit the same invariants generated by the trace of the triple now product of lax matrices of this monodromy. And these are the invariants, J1 and J2. And we can also observe that when we reduce in the levels Z equals 0, then we obtain the previous invariance of the Adler map, okay. We can prove that the maps R1, R2, R3 can be written as products of involutions, so which admits the same invariants. Okay, so these are R1, 2 is just the extension of Adler's map in as we defined it before, and all these satisfy all two invariants. Okay, and the proof is fairly easy and straightforward. You know. It basically makes uses the fact that this is a solution of the Yang-Baxter map. Okay, Yang-Baxter equation. Similarly for R3, we get the same things, and in general we can prove the following: that the maps R1, R2, R3 commute with each other, and additionally satisfy this relation. Here I mean composition, right, of maps. So the proof, again, is not particularly complicated or difficult. You know, it's just a combination of the fact that R is involutive and satisfies the Yang-Baxter equation. But here is a remark which I want to make in order to connect with another work of Adler. So basically, we can see that these maps, so R1 and inverse of R2 and inverse of R3, they are birational, they commute, they have two invariants, and also they satisfy this thing. So they form what Adler calls triad maps. We call it Adler's triad maps, or an Adler's triad. And this actually, so this work of Adler was very important because it generalizes the QRT construction of integrable maps in 3 dimensions. And it's very well algebrogeometric and very neat, actually, at the end, the generalization. But of course, the starting point in Adler's paper is basically the invariants and how we can construct maps that leave this invariant, well, these functions invariants. But there is no mention about lax representations or integrability or something like that. So here, starting from the lax pair, we have refactorization problems by definition, right? So if we plot the orbits of, let's say, R1 for the parameters A equal 1, B equal 2, and C equal 3, and for different initial conditions and for many points, we get periodic orbits. Yes, we get periodic orbits. Now, of course, it's difficult to give a general description of the orbits for different values of the parameters. This is kind of an algebrogeometric problem. But I would say that by using experiments in Mathematica, we can see that this picture is quite stable in perturbations of the parameters. Okay, and for initial conditions. Of course, there are initial conditions where the orbits go to infinity, but there are actually many which are periodic. Okay, so the orbits lie in the intersection of the level sets of J1 and J2. So J1 is just a plane in 3 dimensions. The J2 looks like this one level set. So basically, I would say that the invariants are in this neighborhood, but also they can be also escaping at infinity, right? We can prove some statements about these maps. So they are measure preserving. And how to prove this? Basically, we can prove that the simpler maps R12, R13, and R23, their Jacobian determinant is equal to -1. But since these two are can be factorized in products of these two, then they will have Jacobian equal 1, which means that they preserve the Euclidean volume norm. Okay. So in fact, they are volume preserving, to be more precise. And we can prove the revealed integrability. So this is the Poisson bracket, and we can just, it's straightforward calculation. You can see that J1 commutes with J2, Poisson commute, and that these maps, the R12, R13, and R23, they just don't preserve the Poisson bracket, they anti-preserve it in some sense. So the product of these two, they will preserve it. So altogether, R1, R2, and R3, they preserve the Poisson structure. Okay. And J1 is the Casimir of the Poisson bracket. And while R1, this is the remark that R12, while they're involutive maps, they're not integrable in the Liouville sense, okay, because they don't preserve the Poisson bracket. Now I wanted to make a few comments about these maps in relation to continuous integrable dynamical systems, so integrable vector fields. So let's consider this dynamical system, this dynamical vector field, and this admits the same invariants J1 and J2. And basically this didn't came just from nothing. So basically this is this, right? And you can see, you can think geometrically, and you can see that the flow generated by this vector field will be always will lie always in the intersection of J1 and J2. Well, I mean, this is basically comes from the Naboo bracket in 3 dimensions and preserves by construction J1 and J2. We can write this vector field in the following way, right? Which P1U is just, well, it's a Poisson structure, it's a Poisson matrix, and the same holds for P2. So basically this system is integrable by Hamiltonian, okay? And phi is just the usual isomorphism between the R3 with a cross product and SO3. Now, for this map, for this dynamical system, the maps R1, R2, R3 can be thought as numerical interpolation of the real flows, of the real flow. And in fact, some quick experiments that I made, actually they show that they have quite good accuracy, like of the order of 10 to the -6. So, and actually for long integration times, and actually they preserve exactly the invariance by construction. So this has interest from geometric integration point of view, and also can make a comment in comparison with the Hirota-Kimura-Kahan method, because we're talking about a quadratic vector field. So the Hirota-Kimura-Kahan method can be applied here easily. So this map here, but this map now it fails to, while it has very nice properties, it fails to preserve exactly the invariance, and actually also the periodic orbits are not preserved. So in this sense, I wouldn't say that for this vector field, the Hirota-Kimura-Kahan method is ideal, but still it might preserve some kind of deformations of the invariance. Well, I mean, I still haven't understand what's going on here. So let me talk about some generalization. So how much time do you have? Maybe 10 minutes. Yeah, okay. So let me now say about some generalizations, and this generalization has to do with higher dimensional maps. So for example, let's consider this lax matrix and this refactorization problem. Here, in some sense, I'm abusing a little bit the notation, because the L matrix does not depend, it depends on x1 and x2 on two variables, but not as a vectors, right? So there is a difference actually. And I will show you an example later that there is a vectorial dependence on the lax matrix. And actually this changes things a little bit, but okay, this may be fine detail for the time. So this refactorization problem defines what's known as Adler-Yamilov map. So again, a birational map. Here, here from the trace of monodromy, you can find these invariants. There is a Poisson structure. Now we're in 4 dimensions, so this comes basically from a symplectic structure. It's also volume preserve. The map preserves volumes. And here you can also do this. You can play the same game. You can consider the triple refactorization problems, and we'll find the 3 6-dimensional maps, and we can prove their integrability. But I will not give any details here because the expressions are quite messy. Now, let me show you an example of where you actually, in the lax matrix, you have a vectorial dependence on the variables. And this comes from the Darboux matrix of the vector mkdV and the vector sign Gordon equation. So it appeared in my work with Sasha Mikhailov and Jingping Wang, and also with Panagiotis Adamopoulou in the previous talk, actually, as a Darboux matrix. So here the variable x is just appears as here in this. It's a vector, it's a subvector of a bigger vector, and comes here. It appears here. So if we consider this refactorization problem, it will give an involutive Young-Baxter map. And here is actually the qualitative difference that I talked about before. So since here you have a dependence on a vector, so all fields are in the same footing in some sense, you indeed get an involutive map. While before the Adler-Yamilov map, it's not involutive. Okay. So here we have a Young-Baxter map from the sphere times the sphere to the sphere times sphere. So this is the map. It has a scalar invariant, but also a vector invariant. And well, if we want to simplify things, we can consider n equal 1. So we can go to S1 and then make the stereographic projection and obtain this map here. Okay, so this is another Young-Baxter map in 2 dimensions. We can talk now about the generalization of the parametric Young-Baxter equation, or we can talk about solutions of these equations, the parametric and Wanning-Yang-Baxter maps. And basically, it's there are maps which satisfy this equation. Basically, here you can have a different maps. So not necessarily all maps can be the same. So in this case, if the maps are equivalent to these refactorization problems, or they come from these refactorization problems with different lax matrices, then we say that they satisfy the parametric and Wanning-Yang-Baxter equation. Now, observe that here you don't have the same symmetry that I talked about before. So these maps are not necessarily birational, but in fact, in the examples that we will discuss, they are. This has come from this joint work with Sotiris. So we consider these matrices, and we obtain these S, R, and T matrices, birational maps. These are not involutive, so they have interesting dynamics. They are parametric at Wanning-Yang-Baxter maps, birational. They have polynomial and rational invariants. They are symplectic, Liouville integrable. They have very nice properties. But also we can play the same game and consider triple refactorization problems related with them, or higher in some sense, and perhaps consider families of higher dimensional families related to these problems, and maybe their dynamical related dynamical systems. So these are some kind of ideas, some open problems to talk about the integrability of these higher dimensional maps. In principle, the right way to do it is by using R matrices, or maybe some kind of Sklein bracket. And these are some things that we're looking now, and together with maybe generalization over Grassmann variables or non-commutative variables in general. Okay, so with this, I would like to end the talk here.
Okay, thank you very much.
Yeah.
Are there any questions or remarks? There is one question, 1 second from the audience by Dimotalayev.
Hi, George. I
Hi.
have one question about the formulation of the trifactorization problem. From the point of view of the tetrahedron equation, the more natural trifactorization problem is completely with the completely transversed parameters. In your version, it is not the case. Is it equivalent, or why the completely transversed version is not natural in your approach?
It doesn't have to do with natural or something like that. I think it's a different thing. Tetrahedron equation is completely different kind of beast, right? So here we just take higher dimensional maps and basically as compositions of Yang-Baxter maps. So usually solutions of the tetrahedral equation appear as a kind of, well, it has to do with tensor products, right, of matrices, if I'm not mistaken.
It's not completely the case. You can consider the set theoretical solution, but it's just the form of the equation. Could you? So is it natural for you to make the same form of the trifactorization problem? You understand the completely transversed parameters. Is it natural or not?
Natural. Well, I would say that. So these problems are kind of naturally to be kind of considered like all together. Like it's kind of, I would say, the same with the hierarchy of integrability, of integrable systems, right? So here you get refactorization problems like 2 or 3 or higher order, and you get the hierarchy of integrable maps. So this is how I see it, right? So for me, this is kind of natural. I'm not saying that the lax formulation of tetrahedral equation is not natural, but I think it's a different kind. So I don't think that these two are related in some sense, or I don't fully understand then if there is a relation.
Okay, thank you. So any other questions or remarks?
Can I ask something, Sotiris, if possible?
Okay, yeah, Theodoros.
So regarding these periodic orbits, hi, Yorgos, yes, these are they indeed periodic or quasi-periodic in a closed curve?
Well, this is what I mean. Yeah. Well, the continuous solution of the dynamical system is periodic, right?
So this is a three-dimensional map, is it?
Yes, yes.
So yes, so I guess the continuous has the same integrals.
Yes.
So basically, it can be restricted to the Casimir level sets. So then you have two-dimensional system with one integral. So basically, this shows immediately that indeed your map should rely on the exact integral curves of the continuous system because it is reduced to one-dimensional map.
So in this case, it is periodic because let me show you. So
so it is periodic. So
I think so, but let me argue a little bit about it. So here you see the invariants, right?
Yeah.
So basically the orbits are the intersection of this linear invariant with this cubic one.
Yes.
Or in other words, if you eliminate the variable z, you will get a cubic in 2 dimensions. So this is.
But as a map, okay, it will be in one dimension in a closed curve. But as a map, will it be? I mean.
Well, but that's the thing. I believe it will be parameterized by Weierstrass functions, right? So it will be.
So there will be a period. Which.
Yeah. Okay. So I mean, there is an algorithm of how to make this the intersection which is an elliptic curve to the Weierstrass normal form, and I think there you can parameterize everything in Weierstrass and derivatives, right?
Yes, but you cannot. You haven't computed the period.
No.
Okay. Thank you.
No problem.
So any other questions or remarks? Okay, in which case, thanks again, George. Sorry, is it? In which case, thanks again.
Thanks for having me.
The last speaker for today is Spiridula Sklaveniti from the Hero-Watt University. Spiridula, can you hear us?
Yes, can you hear me?
Yes, perfectly. So
okay, let me share my screen then.
Yes, please.
Okay, can you see?
Yeah, we can see your slides.
Okay, so let me full screen. Okay. Firstly, I would like to thank the organizers for giving me the opportunity to present our work. Actually, this is a joint work with my supervisor, Professor Anastasia Doiku, and it's on a discretization of the NLS type hierarchy. So we are dealing with integrable equations. We know that there is not a strict definition what integrability is. So there are some properties that the equations may obey. So,
sorry, we cannot see we see a black screen. Maybe the solution is to exit full screen.
Can you see now?
Yes, we can see now. I think it's better if we leave it like that.
Yeah, I don't know what happened with the full screen.
Yeah, when you turn to full screen, it shows a black screen. So.
Okay, so you haven't seen anything so far?
No, just the first slide.
Okay, but you heard me.
Yeah, we heard you. Yeah.
Okay. So we are dealing with integrable equations, and as I said just before, we know that there is not a strict definition for what integrability is, but we use some properties that equations may have, and some of these are the existence of a Lax pair, namely to represent an equation with a Lax pair. to be able to apply the inverse scattering transform, if we can find infinitely many symmetries or conservation laws, and of course, if we are able to give explicit solutions via the Backlund transformation, then we can say that our equations are integrable. So our equations of interest here are those that associated with the NLS hierarchy. Here you can see the continuous equations, the nonlinear Schrödinger equations with physical applications on water waves, fiber optics, and so on. The Cordovec-de Vries equation with applications on shallow water waves, acoustic waves on a crystal lattice, which is given by this equation here. The modified Cordovec-de Vries equation with applications again on traveling waves and so on. Here we are more interested in the discrete equations, actually on the differential difference equations of the NLS hierarchy. The first member of the hierarchy, we will see later that it is the discrete self-trapping equation with applications on nonlinear dynamics of small molecules, the motion of an electron in a crystal lattice, and so on. And we will see the generalized form of this equation, actually the matrix form of this equation, and its solutions, of course. The next member is the discrete NLS nonlinear Schrödinger equation with applications on quasi-particle motion on a dimer, on nonlinear wave guides in nonlinear optics, and so on. And again, we will see the matrix form of this equation and its solutions. So the main aim of this work is to derive solutions of such differential difference equations using associated linear equations. Actually, we can solve the associated linear equations, and having these solutions at our disposal, we can derive the solutions of the nonlinear equations. How can we achieve this? I mean, to derive the solutions, we can apply dressing schemes like the Sakharov-Shapard dressing scheme, the Backlund-Darboux transform, and so on. Apart from being interested on deriving the solutions, we are also interested on constructing the hierarchy. Actually, to construct all the lax pairs, which is a criterion for integrability, and identify the associated integrals of motion associated to the hierarchy under study. Here we focus on the generalized discrete NLS model, nonlinear Schrödinger model. Probably some of you have already heard about the Ablovitz-Ladikh model, which is the most well-studied model. But here we focus on the discrete NLS model. Actually, we found that the generalized discrete NLS model is the more natural discretization from the algebraic point of view compared to the Ablovitz-Ladikh model, the discretization of the continuous case. So we introduce the lax pairs Lj and Vj with N here we denote the time flow, the members of the hierarchy, and we defined psi j to be the solution of the following auxiliary problem. You can see here that the spatial part has been discretized while the temporal part is still continuous. The compatibility condition of these two equations is given by relation 1, from which we can derive the discrete equations of motion for every time flow Tn. Here, our starting point will be the L matrix. So given the L matrix, we will construct the hierarchy by finding every Vj. And of course, to find, we will find the solutions. So the starting point is the L matrix, Lj matrix. In the case of the discrete nonlinear Schrödinger model, is given by this matrix here, where xj and yj are n by m and m by n matrices respectively, and nj is given by this relation here. So we want to identify the dress quantities Vj for the discrete NLS hierarchy. We remark here the Ablovitz-Ladik model. You can see the difference between these two matrices. And actually, you will see later where we will find the equations of motion that when we are dealing with the discrete NLS model, we will have the forward difference scheme, while on the when one is dealing with the Ablovitz-Ladik model, on the difference equation, we see the central difference scheme. So let them be the Darboux transform such that when we apply the Darboux transform on a given solution, we can find another one where both psi and psi hat satisfy the auxiliary problem with L, V, and L hat, V hat lax pairs respectively. And applying the Darboux transform on the auxiliary problem, we can find the Backlund-Darboux relations, the following Backlund-Darboux relations, which are the key points for finding the solution and constructing the lax pairs. So we consider two types of Darboux transforms. The basic Darboux transform, which is given by the first matrix, and the Toda type Darboux transform, which is given by the second matrix. We can apply both Darboux transformations in order to find the dressed quantities Vn and the solutions. Here I will present the basic Darboux transform in order to find the hierarchy, and the Toda type Darboux transform in order to find the solutions. You can find more details on the paper I and my supervisor have published recently. And I have the reference on the last slide. So before we proceed in finding the dressed quantities, the Vn of the lax pairs, we derive the associated conserved quantities, which is another property that guarantees the integrability. So we define the monodromy matrix to be the trace, we defined the transfer matrix, to be the trace of the monodromy matrix, which is given by the product of the L matrices on the sides. And we expand the logarithm in order to find the local conserved quantities. we expand the logarithm of the transfer matrix in powers of lambda. So here we report a few conserved quantities. The one that corresponds to the Hamiltonian and the other one that corresponds to the momentum. And we managed to find the general recursion relation for the local integrals of motion. So for each k, we can find all the conserved quantities by this recursion relation. So back to the Darboux transform, we consider the basic Darboux transform and recall here the Backlund-Darboux relations. As we mentioned earlier, these are the fundamental relations we will use for our goal. So from the first relation of the Backlund-Darboux relations, if we can say that x hat and y hat are the trivial solutions, we can find a set of relations from which we are able to find the solutions, the corresponding solutions. You can see that, for example, bj is equal to minus x, which is one of the fields of our solutions, and cj is yj, which is again one of the fields of our equations. So again, let L hat and V hat, we consider that L hat and V hat are the bare-lax pairs, and by saying bare-lax pairs, we mean that all the fields are equal to 0. So X and Y are 0. And the matrix sigma is given by this matrix here. And we consider also that the dress time components of the lax pairs can be expressed as a formal series of powers of lambda. And we need to identify the quantities wk for each time flow n. Here we report the first few examples for n equal to 1 and n equal 2. Recall the compatibility condition we saw at the beginning in order to find to extract the equations of motion. So for n equal to 1, we find that v j1 is given by this matrix, and substituting v and l into the compatibility condition, we find the matrix discrete self-trapping like equation. I have omitted here to write the second equation, but it is exactly the same, but with y and some plus instead of minus here. For n equal to 2, we find vj2 to be given by this matrix here, and substituting vj and lj into the compatibility equation, again, we find the discrete matrix nonlinear Schrödinger equation and corresponding equation for yj. So in this way, we can construct all the vjn, therefore all the lax pairs for the discrete nonlinear Schrödinger hierarchy. Of course, we can use the fundamental, we can apply the fundamental Darboux transform in order to extract the solutions for for these equations, but I have omitted here in order to present the other way, I mean, to apply the other Darboux transform, and this is the Toda type Darboux transform. Recall here the first of the Backlund Darboux relations, and let the Toda type Darboux transform to be given by this matrix here. L hat is again the bare lax operator, but in this case, we cannot set x hat to be equal to 0 because bj then would be 0, and this is something that we don't want, of course. So here we, considering the following answers, we find that x hat satisfies the following linear equations. Here we are able to set x hat, to set a y hat equal to 0, but not the x hat. So x hat satisfies the linearizations of the equations we found earlier. And the first one, for example, is the discrete transport equation. The second one is the discrete heat equation, and so on. So now, having at our disposal the solutions of the linear equations, we will find the solutions of the nonlinear ones. So we consider the generic form of solutions of the linear equations, and we can observe here also the dispersion relations from we can found from the linear equations. So because x hat and y hat and y here are connected with x hat, we can solve these relations and find the solutions of the nonlinear problem, which are given by these relations here. So we choose two simple solutions. If we choose that x hat is given by this relation here, then we can find x and y, the solutions for the nonlinear equations with the corresponding dispersion relations, of course. And we can see here the form of the solutions. Now, if we choose another simple solution with the corresponding dispersion relations again, then we can see the soliton solution for the NLS equation. So we can say here that for different initial profiles for the xj, we can find general distinct solutions for the nonlinear equations. I think I was super fast here. The next step, of course, on this work is the generalized fully discrete case. The scalar fully discrete case has already been done by my supervisor and a colleague of hers. So we are interested in the generalized fully discrete case, I mean the matrix fully discrete case. Another step is to apply the dressing method to hierarchy of other equations, let's say the Boussinesq hierarchy. And of course, one can apply non-periodic boundary conditions because here we have applied everywhere periodic boundary conditions and see how it worked with non-periodic boundary conditions. Here there are some references, and thanks a lot for listening.
Okay, thank you very much, Spiridula. Are there any questions or remarks?
May I ask a question?
Yes, sure.
The fundamental property of the nonlinear Schrödinger equation and this derivative, etc., is that it's a system of two complex conjugated equations. Now, I wonder if your discretization, satisfy this condition. I mean, if you have initially your functions are complex conjugated, then the dynamics, according to your discretization, will keep them complex conjugated, or this fundamental.
Yes, this is a generalized form.
What means generalized form? I ask simple question. If you have two complex conjugated initial conditions, whether your dynamics keep this property in time, or
yes. I mean, what I mean by generalized, I mean that here, where we firstly consider the L matrix, here, we could choose that Yj here is the complex conjugate of X. Is this your question, if I understand well?
Right. So, and your dynamics later on, I mean, the equation really, keeps this property. That is a true reduction. Okay.
Okay.
Thank you.
Any other questions or remarks? Again, in which case, thanks, I guess, again very much, Spiridula. Thanks all the speakers for your talks today and all the participants of the conference. So we're coming to an end. I just wanted to say that all the material of all talks, the talks on YouTube are available on the same links I was sending you during the week. So they were automatically recorded on the YouTube. Regarding the talks on Zoom, I will make available all the material during the next week, and I will send you the links to them again. And I wanted also to remind you that we are planning to publish works related to the conference talks to the Journal of Theoretical and Mathematical Physics. So I will send you again the instructions of submission instructions. The deadline is 30th of November. So thanks again very much all of you for the participation, and I hope that next year the situation with the virus will calm down. I hope that Sputnik will save the world and we will have a normal meeting with physical participations here in the city of Yaroslavl. So thanks again very much, and have a nice day, everybody. Cheers.
Satiris, thank you very much for a nice conference and a lot of efforts you spent to organize it.
Thanks very much, Andrei.
Thank you.
We are waiting you here next year if things calm down.
Yes, I hope so. Yes.
Yeah.
I am also waiting for this.
Yeah.
Okay.
Right. Okay. Have a good evening then.
Good evening.
Bye-bye.
Bye.
Thank you very much for this nice conference. I enjoy
hello,
it.
Norbert.
Yeah,
Thanks
hello.
very much.
Thank you. Thank you. And
we're also waiting you here next year if things calm down.
Okay. Thank you very much. And congratulations again.
Thank you. Thank you.
You're welcome.
Sotiris.
Hi, Pavlos.
Sotiri?
Thank you very much, Sotiris.
Okay, thanks. I saw you waving, but I couldn't hear the sound.
Okay, here we are. All,
Yeah. Yeah. Finally, all of us thought you were in different rooms and cities.
Well, not different rooms.
The different cities, yeah.
Wait a moment.
So you have to use the magic of editing to cut Yota saying Yorgo come.
Yeah. And I swear we saw a ghost coming.
You should have seen Yota's expression when she realized that actually she is still with camera and microphone on.
I've seen my expression of disappointment. I was like,
When is the deadline for the submission again? Sorry.
so there you're muted.
Yeah, unmute yourself.
Yeah, of course. I'm muted.
And stop recording. Stop recording.
Stop.